C times 1 over B. Oh yeah. So the second one, there we go. All right. So thanks everyone for your help on that one. So we're about halfway through time-wise. Let's see how we can do with this problem. So this is, I saw this is a kind of common configuration. So we have a triangle with point P and a circumcircle. So there's like a lot of well-known theorems about Symmedians with this configuration. So you have any point P. So I think this problem was probably based off the Symmedian configuration with this. I just don't know exactly how to apply it. But so AP meets the circle at a point D, and BP, so this is E and F, and M is the intersection of the circle AEF with gamma, or omega, not gamma. Whoops, what happened there? Okay, let me make P a better point so that there we go. Okay, so this is M. And T, and then we draw the tangents at B and C. We move point P around. Yeah, I just want to be able to see the intersection of the tangents. And U is the second intersection of TD with a circle. Interesting. We want to show the reflection of U over BC lies on the circumcircle of DMP. So let me make this look a little farther from M, something like that. So this is point U. Oh, nice. That has the whole calculation. XB is equal to I like it. I'm reading through DAT's calculation. So XB plus YC plus ZA.
It looks like complicated when it is on the chat, but yeah, when you write down, it would be more easier. Just after our session, you could look through over it. Yeah.
I'm just gonna copy paste it. So let me delete this. Sorry, one more second. I'm just going to separate all the equalities. So XB plus YC plus ZA. Okay, I'll look through it a little bit more after the session. So back to this problem. There we go. Oh, wait a sec. What just happened here? There we go. All right. Okay, so draw that, that. So TD intersects the circle at U. So it looks like we have some harmonic quadrilaterals. UBDC is harmonic. I want to show the reflection of U over BC lies on the circumcircle DMP. Interesting. This problem feels like a lot of theory. It feels like if you know enough about like Symmedians and stuff, then this problem would be easy, but I'm not sure. So yeah, UBDC is harmonic. Is there anything we can do with that? So I know there's a theorem that says if we let DE and DF meet this circle at 2 points, then if we connect B and C to those points, they'll intersect on the Symmedian, which is AT. But yeah, I'm not sure how much we can do with that. But yeah, this is really interesting because P can be any point it wants, basically. I think the diagram looks nice when P is like lower like that. But we don't want U, we want to make U a little bit, yeah, maybe something like that. So wait, where does E and F get used? Oh, because it's M, it's used to define M. AU, BC, and EF concur. Okay. Because if we let AU intersect BC at a point, then we could show that's in harmonic conjugation with this point, I'm guessing. Is that kind of how you're doing it? Okay. I think in order to draw that point, I have to first hide this and then draw the point and then unhide it. Oops. So we want to show BGHC is harmonic, and we could try to project through U onto the circle, and that would be the same as saying AB. Wait, yeah, are you sure? Let's see. Oh, I looked. Let's see.
You project through A, then it's true.
Project through A. Okay. Yeah, because you want U. Yeah. All right. Sounds good. So yeah, so then because U, B, C, D are harmonic. So yeah, so A, U, E, F, and B, C are concurrent. All right, so we want to show that if we reflect U over BC, it lies on that circle. M is the McKell point of BFEC, right? Yeah, BFEC. So we have a couple other cyclic quadrilaterals then, right?
Can you reflect U with respect to BC? Maybe we can
Yes.
find a property about it.
Yes. So I think that means like MHEC is cyclic, is that right? HMEC?
Are U prime P and BC parallel?
U prime BC?
Yeah.
Or-
U prime T and BC parallel.
Oh, U prime T and BC. Okay. I don't think so. I'll move stuff around, but yeah, that doesn't look parallel. No. Are U prime D and E collinear?
It wouldn't be symmetric.
If U prime D and E collinear, so U prime D and F is collinear too.
Yeah, I was gonna say it would be the same argument. So is there one more cyclic quadrilateral? I don't know if it really helps drawing all these cyclic quadrilaterals, but I think there might be one more. So we had HMEC.
I think it's confusing.
Yeah.
Can you draw U prime P?
U prime P, yeah. Maybe that passes through the midpoint of this arc.
Yeah.
I don't think it is, but let me.
Special point.
But maybe it's some other kind of a point. Yeah, so it's not the midpoint. Anmal said maybe HM and I are collinear. I'm just kind of making guesses here. Yeah, it looks like it, doesn't it?
Well, we can use that maybe after that power of point with respect to.
Okay, that's interesting. Oh wait, no, I don't think HM and I are collinear. So now that I just moved it now. So let me delete this circle because it's a little confusing. And let me hide some things. Oops.
Actually, you can delete I. It seems useless.
Okay. We could delete T.
No.
Okay.
No, please don't delete T.
Okay.
Yeah.
I'll leave it. But yeah, because once you know, yeah, I'll just leave it there. Is HAC a right angle? I don't think it should be, because this circle could really, I always measure these angles wrong. So let's see if I do it acuter. I know I do it the other way, but yeah, no, it's not a right angle. It's very close though, but only because the diagram is that way.
Sorry, you cram the pass through the BC, the midpoint of BC, I think.
Draw the midpoint of BC. Oh, you think U prime D and I are collinear? Interesting. Yeah, it looks like it. If HE and DU intersect at Z, then is ADEZ cyclic? Let's see. So if I call this point Z right here, you want to see is ADEZ cyclic? It doesn't look like that would be cyclic, right? Just by looking at it. Maybe you meant AD. Yeah, I'm not sure. But yeah, let me know if you can find UD and I are collinear. That's true by the Symmedian theorem. Okay.
Oh yes, I have remember this lemma. So if you reflect D over BC, you will have the U Humpty point. If you reflect, yes, and we all know that the Humpty point of triangle BUC is lies on the median of U. Yes.
Okay, so yeah, D prime is the Humpty point of BUC. Interesting. So that's like a well-known fact. And so basically, if you use that fact, then that kind of proves that U prime, D, and I are collinear. So the Humpty point, it's the reflection, I'm sorry, it's the perpendicular from the orthocenter to the median. So really, let's say you have like a triangle. I could just draw it really quickly. But if we draw the orthocenter of this triangle, so I'll do it really quickly here. So really there's three different Humpty points, but you take and then what I'm going to do, so N is the orthocenter of that triangle. Sorry about that. Trying to close it. Oh no, what just happened here? Just want to get rid of this. There we go. So sorry. So there's a J Humpty point, an N Humpty point, and an L Humpty point. And it's the foot of the perpendicular from the orthocenter to the median. So N is the orthocenter of this triangle. So Q would be the J Humpty point. So that's the definition. And there's a lot of different properties. I'm not going to go into all of them right now. But if you search it on Google, you'll find a lot of stuff related to it. So Q is a J Humpty point, and then there's also a K and an L Humpty point. All right, so D prime is the Humpty point of U. And so D prime lies on UI. And so therefore, by reflecting over BC, U prime, D, and I are collinear.
ID times IU prime equals to IG times IH. Maybe this can be useful.
Okay, so that's cyclic basically, right?
Yeah.
Hmm. Yeah, that circle looks like it.
Can you draw IP?
IP? Yeah. The whole line or just a segment?
Yeah, whole line.
Okay. Oops.
Okay. It won't be useful, I guess.
Okay.
You can also delete the circle, the new one.
Right. Okay, so once we know that ID and U are collinear, I mean, basically we could redefine U prime to be the intersection of, yeah, we're probably pretty close. I should probably hide the circle. I'm just trying to think of the best way to do this. So we want to show that MPDU prime is cyclic, right?
I cannot see the U prime. Can you move the diagram a bit?
Yeah. Let me shrink, there we go. Can you see it now?
Can you move it
Yes. I'll move it.
upside? Okay, that's nice.
All right. I wonder if U prime, P, and D prime are collinear. No. So what if we take DM and P and we reflect them all over BC? Is BMPD cyclic? No, there's no way BMPD is cyclic because BMP and BDP are both acute angles, but maybe BMD prime P is cyclic. Maybe that's what you meant. Oh, but that doesn't look true. But what if we take, because we want to show that DMP U prime is cyclic. If we reflect them all over BC, we get U D prime, and then we need to reflect P and M over BC. So yeah, let's see. What if we trying to use power of a point to show it? Let me draw the circle again. We don't know it exists, but maybe we'll see something special about it. Is there anything special about this circle? Can we use power of a point? Maybe we can intersect ID. Oh yeah, I like that. Okay, so basically if we let U prime be the intersection of ID with that circle, maybe we could prove that angle IU prime B is IUB. Well, That's weird because we know U prime I and B are collinear. And well, so we know the distance U prime B, we know angle IUB is equal to DAC. Or I think you mean, yeah, IUB is TAC by the Symmedian theorem. IUB. Oh, it's all right. Symmedian.
UD is Symmedian in BUC.
Yeah. So IU prime B, like if we didn't know the circle existed yet, we would also know IU prime B is DAC. So we know that DU prime is equal to UD prime in length. Oh wait, I think maybe, so I had a certain idea.
Well, U prime BI and DUC are similar.
U prime DUC and what was the other triangle?
U prime BI.
U prime BI. So I think maybe we could use the power of a point you mentioned because we have IG times IH is ID times IU prime. That's what you said, right?
Yeah.
And then ultimately we want to show
Maybe if we intersect pi with circle,
can I intersect what with the circle?
pi with the circle of PDU prime.
BDU prime or PD?
pi with the circle in the left.
So this point right here?
No, it's pi.
Oh, sorry, my bad. I keep getting it wrong. PI. So right here?
Yeah, maybe it's a special point and we can use power of point.
Let's see.
Can you draw JU?
Yeah,
Symbol.
well, JU.
Is the intersections special?
So maybe this is the midpoint. Where's the perpendicular bisector? Okay, that's not, yeah, it doesn't pass through it. You still want to draw that?
No, you can delete it.
Okay. Okay, so IUB equals DAC. Um, Sorry. All right, I'll keep going on this for like 5 more minutes and maybe we can move on to the next one.
UGI is cyclic.
EUGI. Interesting.
AUGI.
AUGI. Does it pass through M? Huh.
Yeah.
Interesting. How did you get that?
Angle chasing.
Okay.
UIB equals to UCD equals to UAD.
Okay. It can't pass through M. Let's see. AMGI. It looks like it passes through M. Oh,
It doesn't pass through M.
Oh, whoops. AU, okay, so it's just AUGI. It's my bad. So that means if we reflect A prime, then like we could try reflecting A prime over BC. And then this would have to be cyclic. Yeah. Maybe A prime and A prime, U prime, and H are collinear. And these are collinear. Okay, so we want to show angle MPA is equal to angle MU prime D. Is that right? I think so. I'm going to hide this circle. I think it might make things a little easier. We want to show DMPU prime is cyclic. I almost thought about using the power ratio lemma, but let's check the chat. Yeah, let's move on to the next one. All right. Oh, I didn't realize oh, this one looks kind of hard. We only have a half hour left, so maybe I'll check this one. Let me see what else we have. This one looks like it might be easier, so I'm going to try this one. Oops, sorry. So H is the orthocenter of ABC, and then we draw the circumcircle. Okay, so AH meets the circle at point P, and then BH and CH. This is also similar, right? You have a point, you let it meet the circle, and then you draw the other two Chevians. So this is point, I'm just going to do it like this. So EF, and then I'm going to rename that point P. So P is the reflection of H over BC. And then PE and PF. So yeah, this is a very like familiar configuration, right? So it's like a Symmedian type idea. And I think A is actually the midpoint of QR. So PE meets it at Q. Well, actually, now I'm not sure about that. I don't think A is necessarily the midpoint of QR, is it? And then AY, QR, and EF are concurrent. Okay, so I wonder if they're all concurrent on line BC. Not positive, but, oh no, they're not concurrent on BC. So AY, QR, and EF. We want to make QR and EF intersect in a better place, I guess. So how should I do that? I want QR and EF to intersect in a place that I can see better. That's hard to do. How do I get QR and EF to intersect better? I make a tall triangle, maybe? Yeah, I think that makes it easier. It's like taller triangle. Oops. Something like that. Sorry. A little bit taller. That looks good. So QR and EF intersect here. And then I draw segment, and it intersects the circle at a point Y. And I want to show that PY bisects EF. Is that true, or did I miss something? Let me check the chat. Seems like they, yeah, they don't want to intersect. Yeah. Is that PY bisects EF? Yeah, that's true. Okay. So I'm going to make it look better. All right, I see someone just wrote something in the chat. They're concurrent at the midpoint of EF. What's concurrent at the midpoint of EF? So we're trying to prove that this is the midpoint of EF, right? Oh, CR, BQ, and EF concur by Pascal. And is it obvious that they concur at the midpoint?
Yes, just to the similar triangle.
Okay, hold on just a second. So I'll draw CR and BQ, and they meet on EF by Pascal, right? That's what Melek just said. And then is it obvious that that's the midpoint?
Yeah, just do the similar triangle, and let me remember, I forgot. Yes, and this appear in the Vietnam Mathematics Olympiad 2019, and it's a result from a problem in VMO. Yeah.
Ah, okay. So with P equal to H. So, okay, because PG is a Symmedian, I'm sorry, AG is a Symmedian, yeah. So once you know AG is a Symmedian in ABC, and then EF is anti-parallel. Okay, so that means AG is a median of triangle AEF. So okay. So how do you know that FG is equal to GE? And then how do we know that PG and Y are collinear? Okay. So by Pascal's theorem, CRBQ BQ and EF are concurrent. We'll say at a point G, and then by a well-known lemma, AG is the Symmedian of triangle ABC. So, and then EF is anti-parallel to BC, so AG is a median of BC.
Yeah, now we can finish the problem by second Pascal.
Okay, hold on 1 second, so I'm going to type it up. Implies AG is a median of triangle AFE. And so that means FG is equal to GE. Okay, and then you said one more Pascal will finish the problem.
AYPQRC.
AYPQRC. We would have Y, G, and P are collinear. So that would prove that Y, G, and P are collinear, right? So for Vanch's knowledge, the lemma, if you start with any point, so you start with any point H, or so H, it doesn't even have to be the orthocenter, but if you connect A through that point to the circle, and then you connect B and C to the sides of the triangle, so you'd get E and F, and then you draw PF and PE, and then you connect B and C to those points, and they meet at another point, and it says that AG would always be a Symmedian. So we started with the orthocenter, but it could have been any other point, and the final point G that we get would lie on the Symmedian of triangle ABC. Okay, so Y, G, and P are collinear, and that proves that PY bisects EF. All right, I'm going to move on to the next one. All right, so this one's kind of interesting, but it takes a while to draw. That's the only problem I have with it. Let's try this one. So we have the in circle. Oh, this is a problem with O and I. So, oops. C, and then let's draw the circumcenter. O, and that's D. And then AS, OI, and BC are concurrent. So we draw this line, we draw this line, we extend this line. Wait, AS. Oh, I'm sorry. We don't want to do that. We want to draw this point, and then we want to draw the line through A and that. So AS, OI, and BC. Let me make it easier to see. Oops. So that would be point S. And then H is the orthocenter of I feel like I've done something before with the orthocenter of BIC. Where is that? It must be off the diagram. The orthocenter of BI and C. Whoa, H is all the way up there. I didn't expect that. Okay, let's. How do I draw this so that maybe I just got to shrink it a bunch. Because if I make it a taller triangle, then E goes. I think I just want to make it closer to an isosceles triangle. I think that might be better. Something like that. That looks fine. And ATI is a right angle. So basically we could draw the circle with diameter AI, right? So this circle, AGIF. And so that's the Sharkydevil point, right? So this is T. We want to show that DT, H, and S are cyclic. Interesting. Oh, the point H has a lot of properties. Yeah, I know I've seen it before in problems. You probably know more of the properties than I do, but I would not be surprised by that. Okay, so we have, so I think TD passes through the midpoint of arc BC. You could check that. So here's the midpoint of arc BC. So I think AI and TD both pass through it. Yeah. That's the Sharkydevil. And then H is the orthocenter of BIC. So I is the orthocenter of HBC. So if we reflect I, oh, I'm sorry, go on.
Maybe that was the 9-point circle of BIC.
Oh, so if we take triangle BIC, the 9-point circle of it. So
I'm not sure, but I remember something like that. The Sharkydevil point lies on the 9-point circle of BIC or something like that.
Okay, so let's draw the 9-point circle. So that's the circumcircle KLM. So it's, whoops, sorry. L, M. So yeah, it must not be that circle, but maybe something else.
Yeah.
T.
Sorry.
Yeah.
Let A prime be the reflection of A over OI, like
Okay.
OI. We will have A prime DS are collinear.
A prime DS.
Yes. And I don't know that if A prime TH are collinear.
Ah. No.
Oh,
Doesn't.
no. Yeah.
I intersect TD with AE. Yes. Right. So yeah, I could also drop a perpendicular from D to FG, although I'm not sure how helpful it would be. So if we reflect I over BC, it would be cyclic with H. I can delete L. Okay. So HBI prime C would be cyclic. HTDS. Yes. HTDS. How did you know that was cyclic? Oh, that's the problem. Whoops. Does HS cut AC at the midpoint? Let's see. Looks like it might. Yes. Are T, O, and S collinear? No. If I move it around a little bit, yeah, it definitely passed through the midpoint of the arc. So how do we want to show it's cyclic? We could use power of a point. We could use radical. Maybe we want to draw TH. Are TH and A prime collinear? I would be very surprised if that were true. Yeah, that's not true. So I don't think that's the best way to do it. But yeah, I think, did you ask me before to intersect JT and HC? I wonder if BA prime, I wonder if those are concurrent. Let's see. No. Is there another point that we can find on that circle? DTHS. So we know L is the midpoint of arc BAC. Maybe actually we still have to prove that, but we know JTL is a right angle. What if I let me see if these intersect at a special point. DH and TS. If I draw that point, is there anything special about that? No, no. There's nothing really that I see. Huh. We use the power ratio lemma.
Maybe that A prime, I prime, and J are collinear.
Okay. Let's see if that's true. It looks true. But yeah, I'm pretty sure that's true. Good observation. Are those collinear? Did we just miss that? Or is that just a coincidence? Okay, yeah, that's just a coincidence. That's not true. So T and S, we know that they're on this circle. H and S. So wait, H. Yeah, I don't think we can use the power ratio lemma. So we have like these three circles. What would happen if we use the radical axis theorem on these three circles? So we would have BC, H. Oh, we would need to draw this point right here if we did that. BCST. Yeah, and this segment would be concurrent, although I don't know what that does. So maybe we could let A prime T intersect that circle again. It doesn't pass through H, it's just a. So yeah, like if I let it intersect it at this point, and then we could try to show that H lies on that circle. We can try to show HAIS is our cyclic. Interesting. I didn't think about that. Okay, I'm going to delete point M then. HAIS. This looks a lot like the power ratio lemma. So we want to show angle AHI is equal to angle ASI. How did you end up finding that HAIS would be cyclic?
Just by simple angle chasing.
Okay.
I'm going to write it in the chat now.
Okay. So yeah, maybe we should let AI intersect HS. And Mel just messaged me. So, yeah. This would be very hard to draw in an exam. Okay, angle DTS equals angle JAS, which is IAS. Okay, so we need to show HAIS is cyclic. Yeah, there's that one extra angle. So I wonder, what if we reflect S about OI? So yeah, we can also show it. I don't think this does much, but we could try to show H prime, A prime, I, S prime is cyclic, but that just seems harder. So we want to show angle LSA. Hold on a sec. So we want to show LSA equals HIA. But LSA is LJA. Oh, wait a sec. I think I've proven that because HIA, I'm going to write in the chat, but HIA equals LJA is equal to LSA is equal to HSA. So wait. Oh, whoops, I sent it directly to Animal. Well, hold on. So yeah, so it's an angle chase to show that HAIS is cyclic. So I guess we still have to prove that HS passes through the midpoint of our BAC, but then, yeah, that would solve the problem. So I'm going to write up what we know so far. Okay, so I'll start by saying HS passes through the midpoint of arc BAC. And we still need to prove that. Say the midpoint L. And then once we know that, let J be the midpoint of minor arc BC. So lies cyclic. And then, oops, didn't want that. See if that works. There we go. And then we do the angle chase that you mentioned. So JTS. So if DTS equals IAS, which is equal to IHS, which is DHS. So then we would have DTHS is cyclic. So that would solve it. We just need to prove, we have to show that HS passes through the midpoint of arc BAC. Maybe we could use projective geometry somehow. Because yeah, what if we take, because BLCJ is harmonic, we could try to project it through S onto line HI. So then we get H. Oh, but that's not going to work so well. Or I wonder if BC and SJ concur on this circle. Yes, interesting. So BC and SJ look like they meet on this circle. And so, like if you projected through point S, L, B, J, and C, you would get B, C, E, and M. And then...
Actually, because of the both angles LKC and LCM is 90 degrees, so LKSM is concyclic.
Okay, so LKSM is cyclic.
Yes. And HDC is 90 degrees too.
Mm-hmm. So H.
So we have DHS equals KLS, and both KL and HD is parallel. So HLS is collinear.
Where L is the midpoint of this arc, BAC?
Yes.
Okay. So we define L to be the intersection of those two circles, right? Is basically what you're saying, right?
Yes.
Okay. So let L so wait, do we need point M? Or okay, so let BC intersect the circle LIS at M. All right. And then angle LKM. So you said there were like two right angles. I forgot what they were. So LKM is 90 and LSM. So LKM equals LSM equals 90. And then so that means that J, S, and M are collinear. So I'll put this all the way up here. So come on, sorry.
Okay, now we have JLS equals KMS.
JLS is equal to KMS. Mm-hmm.
Yes. And we also have DHS is equal DMS.
Ah, okay. So DHS is DMS. So we have KLS is equal to KMS is equal to DMS is equal to DLS or D what is it, DHS. So that means that KL is parallel to DH. So that means that L is the midpoint of arc BAC. So and but wait a sec. So K is the midpoint of BC.
Actually, we defined L as the midpoint of BC, I guess.
So
because HD and LK are parallel, And
Okay.
we found that their angles are also equal, so HLS must be collinear.
Okay, so that means that H, L, and S are collinear. Okay, so that means that H, L, and S are collinear. Okay.
Yeah.
H, L, and S are collinear. So let me add another line here. So let L be the midpoint of arc. BAC. But where do we use stuff about the end center? I feel like we had to use that somewhere, right? I feel like we're missing a lot of information here. So L is the midpoint of arc BAC, J is the midpoint of the minor arc. BC intersects that circle at M. And
Then
then
we use it when we are saying HI is parallel to LO.
okay. But that could be true like if I were any point, well,
I'm not sure though. I mean, maybe we're missing somewhere.
let's see. So I'm just going to think about it. I know we're out of time. I'm just going to look at it for a couple more minutes. So BC intersects that circle at M. LKM is LSM, which is 90. So those are collinear. And then we have KLS is KMS, which is DMS, which is DHS. So HDSM. Oh, wait, but we don't know. Okay, so HDSM we know is cyclic. Yeah, but we proved J, S, and M are collinear because angle LKM is LSM is 90 degrees, right? So since LSJ, yeah, so maybe because yeah, I don't see that we use too much about point I. Maybe I didn't have to be, wait, but where did we use point T? We had to do something with point T, right? Oh, because T, wait, so DTS is J, oh, because we use that TD and J are collinear. So we use the Sharkydevil point right there. Ah, this is really nice. So I'll just say down here, note, we used that T, D, and J are collinear by Sharkydevil properties. All right, so I am glad we were able to solve this problem. So I'm just going to finish the session right here. So for everyone watching on YouTube, thanks for watching my videos. If you'd like to join the sessions in the future, they're at 8 a.m. US Central Time on Sundays. So if you want to join them, feel free to email me at mgreenb801@gmail.com. Thanks and have a great day.